And we're now going to move on to Professor Rob Jackson. Now, Rob is talking to us about atmospheric removal of methane. Rob is a professor of Earth System Science at Stanford University. He also chairs the Scientific Steering Committee of the Global Carbon Project, which produces global budgets for carbon dioxide, methane, and nitrous oxide. Now, Stanford University on the west coast of the United States is currently just waking up. So we said to Rob, look, how about we record your presentation? So we're going to play his presentation for you, but he will be with us in the Q&A while he's having his morning coffee. So over to Rob.
Hello, everyone, and thanks for attending. I'm sorry to have missed the event and the chance to interact with you and the other speakers. Thank you to the faculty and staff at the Center for Climate Repair at Cambridge for your help, and to all my lab members who contributed to the work I'll discuss today. I'm speaking about methane removal and restoring the atmosphere. Restoring the atmosphere to its pre-industrial condition is a challenging notion. We're hurtling past 1.5 and likely 2 degrees C global temperature thresholds as greenhouse gas emissions continue to rise. It's challenging when we can't even stabilize emissions of carbon dioxide or methane, let alone drive them to zero. But atmospheric restoration and climate repair go hand in hand. Let's explore how we might accomplish this goal for methane. If you'll bear with me a minute, I'll share my screen. The drumbeat of doom marks today's climate news. We might track a Category 5 hurricane in Florida, peeling roofs off houses like bananas, flooding that raged across Germany and the rest of Europe this summer, the latest California or Australian town incinerated in a fire fueled by record heat and drought, or one more clip of the Great Barrier Reef bleached white and dying. As documented in the report shown here and released a couple of weeks ago that many of us co-authored, global temperatures have already risen 1.2 degrees C. Extreme weather is here, and the emissions gap for both 1.5 and 2 degrees C is as big as ever. We need a new narrative of hope. Well, as shown here, we're at the beginning of the United Nations Decade of Ecosystem Restoration, launched on World Environment Day in June of 2021. So let's begin by defining ecosystem or ecological restoration briefly. For purposes of this talk, it's the practice and process of assisting the recovery of an ecosystem that's been degraded, damaged, or destroyed. We arrive then at the premise for my talk today. The atmosphere is no different than a wetland or a grassland or a forest. Sometimes we try to restore ecosystems completely. Other times, we're trying to restore part of their functioning, not necessarily to put them completely back the way they were. But for the atmosphere, restoring it to its pre-industrial state should be our goal. I'm less interested today in stabilizing Earth's temperature to some arbitrary value, as critical as that task is, rolling the dice on which catastrophes we'll avoid. Temperature thresholds are abstract, 1.5 or 2 degrees C, or heaven help us, 3 or 4 degrees C. Normal people don't relate to them, and they don't provide a narrative that has led or is likely to lead to action. In contrast, we can restore the atmosphere in a lifetime, at least for some gases. We have to. That's my outlook today as an ecologist and as chair of the Global Carbon Project, an international organization that tracks greenhouse gas emissions. Restoring the atmosphere is a challenging suggestion, I admit, but it's my dream. Stay with me for a few minutes and let's explore the idea. A few years ago, Pep Canadell at CSIRO in Australia and I published this piece in Scientific American magazine. We explored the idea of atmospheric restoration. We also examined the role of the US Endangered Species Act, both in keeping species from extinction and in providing a pathway for restoring their health. We wrote, consider the Endangered Species Act. It doesn't stop at saving plants and animals from extinction. It mandates recovery. When we see gray whales breaching on their way to Alaska every spring, grizzly bears ambling across a Yellowstone meadow, bald eagles and peregrine falcons riding updrafts. We celebrate a planet restored. Our goal for the atmosphere must be the same. Well, I begin today from the perspective that the need for removing methane and carbon dioxide from the atmosphere after their release arises from failure. We have flooded the atmosphere with 2+ trillion tons of carbon dioxide pollution, most of it in the last 50 years, even when the danger to life was clear. We need methane removal and carbon dioxide removal because we have not cut emissions sufficiently. Cutting emissions today will always be more useful and a better investment than removing greenhouse gases tomorrow. I read and publish a lot of poetry. This poem summarizes how I feel, will be published in the journal Light next month. It's called Climate Stasis. We waited, delayed, hesitated, procrastinated, prognosticated, obfuscated on thin ice, dawdled, stalled, free-for-alled, protocoled collect, dropped balls, stonewalled, mitigated communities, modeled, dallied, rallied, death valleyed, risked, bet, staked, gamed, gambled, generally wagered all, and broke bad, faith, dreams, records, ranks, and the bank. With apologies to the audience, I'm going to dig into more technical aspects for the rest of my talk. Some of what I'll discuss today comes from 2 papers published yesterday in a Royal Society special feature organized by Ewan Nisbet at Royal Holloway, the University of London. Thanks to Ewan and others for making the methane special feature happen. It has a dozen or so new papers on methane mitigation and removal, and I encourage you to read the papers, some of them by authors in today's symposium. Well, why remove methane? Let's start with that question. Why bother at all with methane removal? Take a minute to read my list of reasons shown here. You've heard some of these from previous speakers, such as Matt Johnson and Peter Wadhams, and I expect you'll hear others from Daphne Weisham of Methane Action later today. For me, the reasons include reducing methane concentrations in the atmosphere to shave peak global temperatures and delay crossing warming thresholds. Methane removal could also provide insurance against runaway methane release from thawing permafrost in the Arctic. And because getting to zero emissions may be difficult in food production, where most anthropogenic emissions arise, we may need methane removal as a backup plan. Finally, as a complement to mitigation and carbon dioxide removal, methane is a far more potent greenhouse gas, and methane removal requires much lower quantities to help with climate, only tens or hundreds of millions of tons instead of tens of hundreds of billions of tons for carbon dioxide. Well, one reason that comes up repeatedly not to do methane removal is its low concentration in air. Methane may be 200 times less abundant in the atmosphere than carbon dioxide, but the minimum work of separation scales logarithmically with a gas's concentration, not linearly. So it isn't 200 times harder to separate methane in air than carbon dioxide. In fact, the minimum work of separation is only about 60% higher for methane than for CO2 in the atmosphere. Moreover, because of methane's higher global warming potential, the minimum work of capture for the same radiative forcing impact is lower for methane than for CO2. In this figure, you're looking at how the minimum work of separation becomes smaller as methane's concentration rises from ambient concentrations of 1.9 ppm in air to 3 ppm potentially in an oil and gas field to 900 ppm in an indoor dairy. It makes sense for us to oxidize methane in higher concentration situations, including the ventilated coal mine gas the researchers here at CCRC are considering. Just to be clear, here's what I mean by restoration in the context of the atmosphere. Methane concentrations today are 2.6 times higher than they were a few centuries ago. As you look at this figure of methane over the last 800,000 years, the atmosphere may not have trees and grasses and diverse life the way a wetland does, but the concept of restoration still applies. Our goal is to put it back the way it was, and ideally for it to be self-regulating. Although methane is harder to remove from the atmosphere than carbon dioxide, we could restore the entire atmosphere by removing only 3 billion tons, compared with 1 trillion tons of extra carbon dioxide in our air. Will it be easy? No. Is it possible? I think so. As I'll show, drawing down methane should also reduce tropospheric ozone pollution too, so it has co-benefits for air quality and human health. So there's a lot to talk about here, methane's shorter atmospheric lifetime, for instance, and the need for recurring removal, but I'll save those topics for later. The global methane cycle is dominated by human activities to an extent far greater than for carbon dioxide. 60% of global methane emissions now come from human activities, from rice farms to the cattle and other ruminants we raise and the waste they produce from oil and gas wells to coal mines. We control the global methane cycle. Restoring the atmosphere requires eliminating such emissions and increasing the sinks that oxidize methane naturally, including hydroxyl and chlorine radicals in air and microbes in soils. Here, you're looking at an inventory of point source emissions. For methane, such maps suggest we should start removal at concentrations closer to 200 ppm or, where possible, even 2000 ppm, and work towards the harder job of the bulk atmosphere at 1.9 ppm. Well, no equivalent of a cumulative CO2 budget exists for methane. Here I'm going to discuss my PhD student Sam Abernethy's new paper, published yesterday with Chris Jones and Fiona O'Connor at the UK Hadley Centre. Seminal research by Damon Matthews and others in the past revealed a linear relationship between cumulative carbon dioxide emissions and temperature change. To do this work, they employed emissions-driven CO2 models. Our research presents, to our knowledge, the first explicit relationships between methane removal and climate impacts using an emissions-driven, fully coupled ocean atmosphere Earth system model. Methane concentrations are affected by the emissions of multiple gases, including other ozone precursors. So the use of an emissions-driven model allows for direct attribution of the effects of methane on climate. Removal is implemented as a negative emissions in the same way that carbon dioxide removal has been implemented in similar studies using shared socioeconomic pathways as baseline scenarios. We use the methane emissions difference between shared socioeconomic pathways, a high emissions future scenario, SSP3 7.0, and SSP3 7.0 low methane. It's the same high emission scenario, but with reduced methane, as shown to the right here. So we use these to create a hypothetical removal scenario that is explicit spatially and temporally. SSP low methane was developed as an alternative methane-specific pathway for the Aerosol and Chemistry Climate Intercomparison Project. Its methane emissions are among the lowest of all SSP scenarios. The scale of removal, roughly 40% lower emissions by 2050, is similar to values used previously by Drew Shingel and co-workers. Drew Shingel, who looked specifically at pollution control measures from 2010 to 2030. From our removal baseline, the low methane gray line shown here, we created a set of removal scenarios by varying the amount removed. We multiplied the low methane scenario by a constant, 25%, 50, 75, 100%, 150% or even double 200% removal for the blue lines in the upper panel. We also altered the timing of methane removal by fixing the cumulative amount removed by 2100, but delaying the start of removal by one or more decades to 2020, 2030, 2040, or 2050, the green lines in the bottom panel. These methane removal pathways are then subtracted from the two baseline SSPs used in this work. Using these contrasting SSPs leads to our modeled scenarios spanning the full range of realistic future methane pathways from high to low atmospheric abundance. Cumulative removal is the most common metric for quantifying the climate impacts of carbon dioxide removal, but total cumulative removal is less applicable here because of methane's shorter lifetime. Removing 1 unit of methane from the atmosphere means there is instantaneously 1 unit less methane today, but this amount decreases in the future. Approximately a decade after removal, half of the methane that was removed would have oxidized naturally, meaning that the effect of removal would only be half a unit of methane at that time. So in this paper, we define a new metric, the effective cumulative methane removal, shown on the left here, to account for the shorter lifetime of methane and allow for a direct comparison with carbon dioxide. Effective cumulative removal is found by integrating the total amount of removed methane that would otherwise still be in the atmosphere, so that which wouldn't have been oxidized. We define another new measure, the methane climate response, the MCR that you see here, as a difference in global mean surface temperature per mass of effective cumulative methane removed. We estimate this quantity to be 0.21 degrees C for effective petagram methane removal. And we similarly define a methane ozone response and estimate it to be 1 part per billion reduction in global ozone concentrations for effective petagram of methane removed. Another application of our work is to estimate the potential of methane removal to reduce the temperature peak that occurs in the low emission SSP1 2.6 scenario. In previous research, methane reduction has been shown to increase the available carbon dioxide budget, meaning that more CO2 can be emitted while still staying below a certain temperature threshold. So we instead consider CO2 concentrations specified by the SSPs to isolate the relationship between methane removal and the reduction of the peak temperature. Our results suggest that the peak temperature is reduced from 2.6 degrees C above pre-industrial in SSP 2.6 to 1.6 degrees C in the low methane scenario, and even 1.4 degrees C in the more extreme double low methane scenario. So it makes a huge difference for the peak temperatures observed. Well, let me step back out now and talk about some model comparisons we've recommended in the second paper. So building on this new modeling work, we also propose a formal methane removal model intercomparison project. We call it the MRMIP, analogous to previous efforts for carbon dioxide led by David Keller. We recommend the modeling studies you see here, looking at the climate, ozone, and other environmental consequences of methane removal at a range of emission scenarios and using multiple models. We need to apply the same rigor for predictions of the benefits of methane removal as is applied for carbon dioxide. Finally, then, here are some broad technology classes for removing methane, including photocatalysts, metal catalysts associated with zeolites and porous polymer networks, and biological approaches for methane removal, including biofilters and soil management. As I mentioned earlier, microbes provide the second largest natural sink for atmospheric methane of approximately 40 million tons of methane oxidized annually. Researchers and companies are growing microbes in slurries that can be applied to high surface area filters to remove methane. They are also evaluating soil amendments to reduce methane emissions and enhance methane oxidation. Microbial and soil-based approaches have been considered the longest of all technology options for enhancing methane oxidation. Iron salt aerosols, discussed by Matt Johnson, are another method for methane removal. Here, instead of moving air across microbes or catalysts, you introduce oxidizing radicals into the air, hydroxyl radicals that provide 90% of the natural methane sink, or chlorine radicals into air to oxidize methane. This method mimics natural reactions associated with mineral dust particles in the atmosphere. I believe Matt discussed this method earlier in the symposium, so I won't cover it in detail. Briefly, you enhance methane removal by releasing iron salt aerosols in the lower troposphere, increasing the chlorine sink 4 to 6-fold during the day, and increasing or enhancing the OH sink at night. Chlorine atoms react with methane 16 times faster than OH radicals do, and the iron present in catalytic amounts could increase densities of chlorine atoms provided by abundant sea salt. So approaches like ISA have the advantage of delivering an oxidizing agent cheaply into the air, but the disadvantage of being harder to verify the mass of methane oxidized. Well, before I discuss active industrial systems with blowers, let's acknowledge the possibility of passive systems, as Klaus Lackner has proposed for carbon dioxide. Here, a high surface area, such as a carbon tree, might be coated with a photocatalyst, such as the approaches Wei Li, Philip Davies, and Sir David King discussed earlier. One such catalyst to oxidize methane is solid titanium dioxide, a pigment used in paints and sunscreens. TiO2 is photocatically active when exposed to UV light and can catalyze the same oxidation reaction that occurs when a flare burns methane. The advantage of passive systems like Klaus Lackner's is to use natural wind currents and not expend the energy needed in industrial blower systems. In a collaboration with Ed Solomon in Stanford's chemistry department, we're working on porous zeolite embedded with metal catalysts, such as iron and copper. Zeolites are high surface area, aluminosilicate minerals used as molecular sieves and in water treatment applications. Scientists have screened almost 100,000 zeolite minerals as potential methane concentrating agents or sorbents. Copper and iron zeolites, methane oxidizing catalysts, are already used to convert methane to methanol, a partial oxidation product with one added oxygen atom instead of two. Zeolites have already been shown to oxidize methane to carbon dioxide, and the ability of zeolites to absorb carbon dioxide from the atmosphere is well known. Researchers have now screened almost 100,000 zeolite structures as potential methane sorbents. Relatively low temperature methane oxidation has been realized in zeolites, such as copper, ZSM5, and iron, with iron zeolites able to oxidize methane at temperatures approaching a few hundred degrees C. However, higher temperatures and pressures generally lead to greater conversion efficiencies. Issues with these kinds of active catalyst systems include catalyst fouling and pressure drop, the extra energy needed to push air through high surface area materials. Active systems also have advantages in that input and output gases can be monitored for co-produced gases, such as partial oxidation products like carbon monoxide. And they can be verified for actual methane removed in the output stream. I think hybrid systems may provide a good compromise. For instance, combining DAC, direct air capture for CO2 removal, and methane oxidation in the same infrastructure makes sense. You pay to move the air once, but remove more than one greenhouse gas from it when you do. In principle, OH or chlorine radicals could also be introduced into the air of such systems in place of metal catalysts on porous materials, eliminating the penalty of a pressure drop. Regardless of the technology used, and you've heard about several today in earlier talks, I think combined industrial CO2 and methane infrastructure makes a lot of sense rather than removing carbon dioxide alone or methane alone. Well, like a photocatalyst, methane is having its day in the sun. The new IPCC report shone a spotlight on the importance of methane mitigation. The new EU-US Global Methane Pledge seeks a 30-30 reduction, a 30% reduction in methane emissions by 2030. It's not enough, but it's a start. We still need to know if methane removal technologies will be commercially viable, and we need them quickly to help us avoid 1.5 and 2C thresholds. Thank you for listening, and I look forward to your thoughts, comments, and questions.